we'll have 4 speakers entertaining us this fine afternoon. And for starters, we'll have Niels Weddy. Sorry.
It's not like the Jedi.
Yeah. Yeah, from ECMWF, and he will tell us about the global non-hydrostatic cloud permitting medium range forecast using the spectral transfer method.
Yeah, thank you very much. So thanks to everybody coming back to look at maybe slightly more contemporary technology, the spectral transform method. And well, I hope to be able to convince you that it might not actually be that old-fashioned as you may think right now. So I should thank also a number of my collaborators, colleagues at ECMWF, some of them experts in computational sciences or experts in wave modeling or in data handling, which is all aspects that you really require when you want to do a high-resolution simulation. And last but not least, not mentioned on the slide, but these are non-hydrostatic simulations, i.e. simulations with a non-hydrostatic IFS, and ECMWF acquired a non-hydrostatic model through the collaboration with Meteo France and its Aladdin partners, and I should very much acknowledge and mention their large contributions in the non-hydrostatic development of the IFS. So let's just start with a sort of current and planned model resolutions. There are obviously uncertainties on this slide. Look at the future. But you see our current resolution 1279, it's a hydrostatic model. And we do envisage that in the next few years to upgrade to a horizontal resolution of T2000 or 10 kilometers horizontally, which will still be hydrostatic. And we have done a number of tests already now, and we do not see any difference changing to the non-hydrostatic formulation other than quite an increase in cost. So here you see the grid spacings. Here you see the estimated time step that we envisage and the estimated number of cores expressed in equivalence of the power 7, which is currently installed at ECMWF. So what you see is that really a 5-kilometer resolution is something that's achievable. I mean, these are estimates based on runs we have done, except for this one, because we just can't afford it. But there are nevertheless reasonable estimates, I would think, with respect to the number of cores we would require in order to run these forecasts in 1 hour. This means to achieve 240 forecast days per day, per real day. So how far can we go with technology that is applied at ECMWF really for the last 30 years? And what we use is essentially a spectral transform, semi-Lagrangian, semi-implicit, compressible, non-hydrostatic or hydrostatic model. So the big questions, as have been mentioned already in a number of talks, is the computational efficiency, but I should also point out the affordability of future MPP architectures, and likewise the accuracy and predictability at convection permitting scales. So the big question really for us, from a strategical point of view, is the spectral transform dead or alive? So just to first start with some simulation that we have done, this was a Norwegian storm Berit, or some call it Xaver, which happened last year in November, which hit the Faroe Islands, which is a little tiny island up here. You could take, of course, the point of view that not that many people live there, so that's not very. The waves that were hitting the shores of these Faroe Islands were really quite large, up to 15 meters, and they had major sort of destructions there. And it's a typical case for November storms, really, in Europe. And so we did a run with our operational configuration, 1279, so about 16 kilometers horizontal resolution, coupled to an 0.25 degree wave model. And you can see on the blue numbers, not maybe that well, so there's 15 meters here, 13 meters here. These are observed buoys observations, and the contours are the sort of maximum wave height that the wave model predicted when driven by the atmospheric model. So this is a coupled run. So the wave model gives back to the atmosphere a roughness and it receives from the atmosphere at every time step the wind velocities and the direction. So when we run this at T 4000 or -1, so T is 3999, coupled to the high resolution 0.1 degree wave model, you can see that in fact the wave height is really well captured, and we get sort of this 15 meters as observed, and we get an overall better match really to the observations. So we did some sensitivity studies and really find that not only the improvement in the resolution of the wave model contributed to this, but also the improvement in the horizontal resolution of the atmospheric model. So when you look at orographic forcings, because I mean certainly aspects when you increase resolution that play into this is the increase in the mountain heights that you resolve, but also the land sea mass that you resolve better. So the Faroe Islands, for example, will be much better represented at the higher resolution. So clearly this plays a role here. So if you look at orographic variance at these different resolutions that we are able to run now, this is 1279. This is our current operational model, and you see that the orographic variance kind of substantially increases and contributes to this additional forcing of the atmosphere as it flows past. Then when you look at the, it's beautiful to create these spectra in a spectral model because, you have them for free, basically. You don't have to do anything. That's fine, sure. So when you look at the difference between the operational 1279 and then the T4000 runs, this is a 10-day forecast of the T4000 5-kilometer run, then you see that you're substantially more subgrid scale, sort of, what would be subgrid scale at 1279, you get substantially more variance here and also here at 200 hectopascal. The spectra look really quite encouraging. What you also see, which I found a little bit surprising, is now this is a resolution at 5 kilometer where you don't really know whether you should use convection parameterization or whether the convection should be resolved by the model. And you just sort of let it happen, especially the deep convection. I mean, shallow convection would be parameterized in both of these. So one of the runs is with convection parameterized, and the other one is with convection not parameterized. So you see absolutely no difference in the energy spectra, which maybe at the first sight is surprising.
And yes, how did you parameterize the diffusion, or was there any explicit diffusion?
There is some explicit, it uses sort of a new scheme I've developed that deals with the aliasing on the linear grid. So this allowed us to reduce the horizontal diffusion quite a bit, but it would still be equivalent to a 1/6 delta T explicit diffusion with a time step. So the time scale of the explicit horizontal diffusion would be 6 delta T with a time step of 240 seconds at this resolution. Then we come to the T8000 run. This is sort of 2.5 kilometers globally, which I was able to run, fortunately, due to the availability of our Power 7 coming online and not any other users on it so far. And you can see that this matches very much the study that Bill Skamarok did on the limited area model. That in the first few hours, I mean, obviously, your initial data now is forced by the real orography at 2.5 kilometer, and your land sea mass is at 2.5 kilometer, and all your land use parameters and so on at 2.5 kilometers. But your atmospheric data, because I have only an analysis at 1279, is obviously at 1279. So when you interpolate your atmospheric data to the new forcing, you get very much a sort of small-scale forcing, so uninitialized basically. And but over the first 6 hours, you start to see that between wave numbers 300 and 3000, they very much adjust within the first 6 to 12 hours, and you get this sort of spectrum. The other interesting thing is, perhaps from a theoretical point of view, that I find an equipartition between the vortical and the divergent energy components of the kinetic energy that would suggest that at least between 300 and 3000, it is not only the divergent motions that make up the 5/3 spectrum in the atmosphere, but it's actually both vorticity and divergent motions that make this up. So it might be of theoretical interest. Apart from the fact that obviously from about wave number 300, we see that geostrophic theory breaks down, because when geostrophic winds have a zero divergent spectrum. So really from about wave number 300, we are modeling non-geostrophic motions.
You're talking about horizontal divergence, right?
Horizontal divergence, yes, thank you. So it doesn't only produce nice spectra, it actually did also produce a very nice forecast. This is a very nice case, actually, the Lota Christmas storm, because it developed very quickly. Now, since at this resolution, understandably, I couldn't run very long, the Lota storm develops within 12 hours. So I could run for 12 hours this forecast. But when you look at the operational forecast, it did also a reasonable job of this Lota storm. And I should point out that the Lota storm, to the detriment perhaps especially to the German weather service, was not a very good forecast at the time. I think they even have claimed a computer bug that they didn't do such a good forecast. But they were not alone. I think pretty much everybody did a very bad forecast of these storms. And so it's a very challenging case, because it's a very rapid development, and it needs high resolution to capture wind speeds, especially over this sort of mid-mountains, mid-level mountain ranges here in Germany, for example, or over the Alps. Also, we see these peaks of wind gusts. This is up to 100 meters per second. So we're talking wind speeds of up to 360 kilometers per hour. Vorticity at hurricane strengths developed within 11 hours or 12 hours, and rushing through a trail of destruction between, coming in from the Atlantic and sort of, going France, Germany, Switzerland, and so on. And wind speeds were observed actually at this, they were observed up to 270 kilometers per hour before some of the measurement stations broke down, basically. This must be anemometers flying off, basically.
Was there a dependency on the data there? Or, 'cause I remember another storm depended on some observation coming in.
They showed some sensitivity with respect to the initial data, but I think this would not be a problem here, because I started from ERA interim, which had sort of a perfect kind of initial state from that point of view. But actually challenging in the sense that ERA interim was only T255 resolution, so very low resolution. So I had both started actually from much lower resolution, and so the scales were building up over these first 12 hours and still produced a very reasonable forecast. The colors are the wind gusts, basically, and the vectors are the wind velocity vectors. So you can still also see one of the issues in wind forecasting in numerical weather prediction, that the surface winds we predict are usually much lower. Like the 10-meter winds, when you look at those, they are much lower than the actual wind gusts that you would measure when you hold out an anemometer. There are huge differences in the wind speed. So how was it possible that we could run these very high resolutions? Now these were the beauty results, and now we do a little bit of techniques and math. Now the expensive bits, basically, in a spectral transform model are, apart from the communications, to which I will come later, are the matrix-matrix multiplications when doing the sums of products between associated Legendre polynomials at all the Gaussian latitudes and associated spectral coefficients of a field, a temperature at a given level. Okay. So we developed, based on publications by Mark Tigert, a fast Legendre transform that exploits essentially similarities of associated Legendre polynomials at all Gaussian latitudes but neighboring total wave numbers. And the essence of the method is that you pre-compute, which only costs 0.1% of the total cost of a 10-day forecast now. We had a lot of issues with this in the beginning. It was very expensive, but now we found a very nice way of dealing with this. The second stage is to compress, i.e. approximate representations of these matrices in these matrix-matrix multiplications for each m. In fact, the parallelization in spectral space is over the zonal wave numbers. They're all independent. And then you apply. So you do this only once at the beginning of the forecast. So then you apply. You can read this in from a file if you want. So then you apply the compressed, reduced representation at every time step of the simulation. So essentially doing a lot less work when you do these matrix-matrix multiplications. So this works like this. You have this matrix here of Gaussian latitudes, field, and vertical level. You call what they call a butterfly compression of this matrix of the at each m, so the m is basically fixed for all of these, of the n and k, multiply with 6 theta and l, and this is your the matrix that you compress. So in the original Tigert paper, they had a lot of effort in terms of how they would sort of deal with this compression. Partly this was because they wanted to mathematically prove that the asymptotic limit from before n to the power 3 went down to something like n squared log n. But since we're not really interested in the asymptotic convergence, we just want to reduce the cost. We didn't do any of these pre-computations anymore, but apply the compression just straight to this matrix. And that saved us major amounts of pre-computation time. So the essence of the method is really that with each level, you double the columns and halve the rows. So you take this matrix at this level 0, and then you build these pairs, like this at level 1, and then you make more pairs and more pairs. But when you look at these new matrices that you make up, they contain not necessarily linearly independent columns. So you can rank reduce those. And if you look at the spherical harmonics for these different wave numbers, in fact, they are all like zigzags basically. In here, you just can't see them because there are so many of them. And if this is plotted for n equals 3,999, but if you do it for n 3,998, it would look almost the same, the picture. And they would represent 2 columns in this matrix. And you can also see that beyond, these are the Gaussian latitudes here, so you can see from the equator to the North Pole, that from a certain point onwards, they're actually 0. And in fact, this is one of the problems when you compute these associated Legendre polynomials, that you have to be very accurate. But you don't really have to be very accurate. The issue is when you compute them, they're computed from recursive formulas. And you have to make sure that this recursive formula has the correct error cancellation so that you can continue to compute them with double precision rather than you have to go to quadruple precision. So there's a nice way, and since Jean mentioned Paul Schwarzschild, he in fact devised a method that allowed us to go to beyond n equals 1,000 by achieving and ensuring this error cancellation. So I should point this out. So the method is really like the pre-computation step. So there's a lot of householding involved, but just to give you a flavor of the code. In fact, this code, the way it is very much from this paper of O'Neill, Wolf, and Roken. It's in this paper. There's like a cookbook how to do this, and you see that you have to basically extract these submatrices, compress these submatrices, and there's some householding and storing involved. And when we just some detail on the compression itself, this is sort of in the paper from Cheng et al. They call it the ID, an interpolative decomposition, which the essence of this is that you have your original matrix Mn, and you make a new matrix Bmk times a Pkn. And the difference between the two, using some norm, should be smaller than some epsilon. So this is your approximation, if you like. So your P contains a k by k identity submatrix, and your k is the epsilon rank of the matrix A. And that's the essence of the compression of each of the submatrices that you use. So then, at every time step, you have to reconstruct basically your original matrix by using these compressed left and right neighbors. This is all stored in some tree, and you go back up, and this would be like the application step of a matrix vector multiply. Now, a matrix vector would be for a single level, but since we transform all the levels simultaneously, it becomes a matrix multiply. So in terms of timings, I'm running out of time actually, as we're talking timings. The floating point operations, as you can see at B799, are substantially reduced with this butterfly algorithm, and also like here with simultaneous transforms of 10 fields, you see a substantial reduction in the cost of at T10,000. And these were like single field reductions, and this is sort of actual simulations. So the non-hydrostatic T8000 simulation, this is for 1 hour, so this is what we save per hour of forecast, if you like, is now less than the equivalent cost of the sort of do-nothing hydrostatic model. So the thing to point out is that the non-hydrostatic model uses twice as many transformations due to an iterative procedure to keep it stable. Now we hope to work on that as well, but at least we have already now reduced the cost substantially in this context. There is one comment here on the communications, in a sense that for different resolutions, now they all didn't run at the, they ran at some research setups basically. So only this one here really ran at the 240 forecast days per day. So this would sort of satisfy the operational requirement. But you can see that the overhead with respect to the communications at the speed that we require is actually quite small. So this 23 is the total cost, including the communications, of the spectral transform method at this resolution, 10 kilometers, for the operational forecast. So there is no question that this is competitive. Now we have to see how competitive this will be in the future, but it's still below 70%, if you like. Yeah, there is a Cresta project. I should really finish with this, right? So this is a lot of work on the communications to reduce the cost of the communications. Just to show you one graph, that's where we are with the operational configuration for which we are going to implement next. What we have here, these numbers, are basically what we're trying to improve on the assumption that it is equivalent to run a T2000 L137 on about 70,000 cores to running a T8000 on 1 million cores. So the assumption is if we improve this to some more perfect scalability, we can run the T8000 with the spectral transform model at T8000. So my summary, the fast Lazada transform is effective, and the spectral transform method is still alive.
So I don't completely understand how you can almost double your resolution going to T2000 and only cut your time step from 600 to 450. Is it because you just don't feel there are short wavelength features moving at high speeds that you have to accurately capture? Or because you have to give up some sort of accuracy by keeping letting your CFL number get bigger for the fastest moving things?
I mean, there are obviously different definitions of accuracy. But in NWP, we formally and foremost, I guess, define accuracy by comparison to observations and by comparison of what we call scores, like the root mean square evolution over the 10-day forecast and the anomaly correlation, i.e. the deviation from climate over the 10-day forecast. And then a study doing a run at 10 kilometers with 300 seconds, i.e. halving the time step, and 450 doesn't give any difference, or we don't see any difference. So based on that, basically, we assumed, or we are quite confident that we could increase the time step. Basically, that's how it goes. You start with something, and then you increase the time step until you start to see that the scores kind of deteriorate. And based on that level, essentially, we have chosen the 450 seconds. So it's not stability.
No, I understand. You're not, but
the last plot you had, are you sure that you're not hitting a kind of strong scaling wall? Are you sure you can really project out to 5 million cores with this 7,999? Because the communication speed, the latency and so is not going to reduce very much in the near future.
It's going to, clearly, this is anyone's guess, to be honest. But there are some very, very interesting developments happening with respect to these new style PGAS languages to which co-array Fortran counts. And basically, it allows us, now currently we cannot do any communications inside the OpenMP region. So the way it works in IFS is you distribute your tasks over MPI workload. But then within each of the MPI tasks, you fold 16 ways into OpenMP regions and do the work in parallel. Now, it is hugely beneficial to be able to do communications as well within those OpenMP regions, which currently is not possible. And that possibility is given by co-array Fortran. And this really cuts the cost of, or the overhead of the communications, because you can hide the communications behind the cost of the computations. And we have some great hope that, in fact, through the combination of hiding the communications plus advances in computer technology with respect to vector technology and GPUs, we can bring down the overall cost further from the cost that is involved in the transforms, i.e. the linear algebra. And so the combination of the two, yeah, we have hope that it will, in fact, also scale to 1 million processes. Because the way the spectral computations are distributed in parallel space, it is really over packages, over groups of communications. So increasing the number of these groups isn't really affecting in a great way. The latency will not in a great way affect these different groups if you just have more of them. Because it's not that everyone communicates with everyone. It's you have the distribution of the levels over the zonal wave numbers. So it's a lot of subgrouping, basically.
It's just the startup time of the communication between these packages, which is fixed or won't change much.
Yes, but we have enough work to do, if you like, to hide that, presumably.
I guess that's a good point of just to stop and maybe take it over and discuss it over coffee. Thanks our speaker again.